Okay, welcome to today's webinar, Coreform Lattice GC, Precise Lattice Creation for 3D Printing. I'm Kimberly. Your presenter today is Greg Vernon. He's the Director of Product Development here at Coreform, and he'll be walking you through Lattice GC, which is our new functionality that just came out in our latest release. I wanted to remind you that we have another webinar coming up next week. It's to talk about one of the other new features in our release, U-splines for IGA model prep in Coreform Cubit. So please go to coreform.com to register for that webinar. Feel free to share the link with anyone else that you know who might be interested. Throughout this webinar, we have a Q&A option. If you look at the bottom of your screen, feel free to ask any questions at any time. We have a relatively small group. This is a kind of narrow focus, and that gives you the opportunity to get lots of questions answered. So please don't hesitate to use the Q&A. We will have some chat responders and some questions we will also stop and answer live. So take advantage of that. And with all of that, I will now turn it over to Greg.
Great. Thanks. So for the agenda today, we're going to talk about what is Coreform Lattice GC, the motivation behind it, kind of just some high level, what are the mechanics behind Lattice GC, how does it work? And then we'll primarily do a lot of demos today. We'll do a couple of demos on designing these lattice parts in Coreform Cubit using the new lattice or U-spline technology in Coreform Cubit. And then I'll show how to get the lattice information out of Cubit so you can use it for additive manufacturing. And then also how to design a custom unit cell in Coreform Cubit. And then we'll have some time for some Q&A. So I'd like to start today with a poll. So let's go ahead and launch this. There's 3 questions about interest in lattice structure parts that you might have. So if you don't mind going ahead and answering whether or not you're more interested in stiffness or bending dominated lattices. And so we've got about a little bit more on the stiffness, which is usually it's kind of understood, but also some questions about what is the difference between those. So we'll give us a few more seconds here to get responses. All right, so let's see if I can share these results. So you probably can, viewers of the webinar can see this on their screen, hopefully. But for those who maybe can't see it, we had 36% said stiffness stiffness dominated lattices, 18% said bending dominated, and then 45% said, I don't know, what's the difference? So thanks for your responses to that. Can you still see my presentation? It's not clear to me if it's still being shared. Kim, do you know if it's still being shared?
Yeah, we can see your screen.
Okay. All right, so to start, Coreform Lattice GC, it's an add-on license to Coreform Cubit. But all free trials of Coreform Cubit also come with this Lattice GC trial license, so that you can try out both Coreform Cubit and Coreform Lattice GC. If you'd like more information about licensing, how to purchase Coreform Lattice GC, you can contact our sales team at sales@coreform.com. And I'd also like to point out where you can find documentation for Coreform Lattice GC in our user manual online. So there's 2 spots for it. I'll show live after I show these, but We have a chapter for Coreform Lattice GC, which is our reference documentation, which gives references just on the commands itself, and then documentation on workflow. So if you're looking for information about how to build these parts, the workflow section is there for you. So just to show that live, on our web page, under the Coreform Cubit header, we can go to documentation and then click on our link for the online help. And then that will pop up the user manual. And then here in the chapters on the left, we can select Coreform Lattice GC and see the reference documentation for this. And then as well for the Cubit workflows, building U-spline lattices. That's where we find this documentation. All right, so now I'd like to talk just a little bit about the motivation behind Coreform Lattice GC. This actually all began for me back in 2015 at my former employer. I was working on a research project in lattice structures and design with lattice structures. And a lot of the tools that I was using at the time could build lattices that were on rectilinear grids, such as shown here on the left and on the right. And one of the issues that I was running into as an engineer was that if I had a part that had a lattice structure that was rectilinear like this, there's a couple of things you can notice. One is that the load paths, in this case, you'd want to have an axisymmetric response. But depending on what angle you were loading at, you'd get maybe a stiff response or then a soft response because you're at like a 45-degree shear angle. As well as you'd have some lattice structures or struts that might have been cut off or trimmed at a boundary. And you might not get the response you'd want at these locations. And so it made it hard to engineer or design parts that had these integrated components because of these maybe non-desirable material layouts that led to non-desirable material responses. So I wanted to be able to engineer desirable behavior. I had developed kind of a preliminary implementation of this compliant lattice structure technology based on traditional meshing tools that I had at the time, traditional fine element meshing tools at the time. And they would lead to interfaces between unit cells that would have these kinks in them. And these would, again, lead to poor response with stress trying to flow. We get stress concentrations at these locations. And as we went to, as Coreform licensed this technology to partner with my former employer to develop this into a commercial tool, the U-spline technology allows for these smooth interfaces between lattices, which leads to a better stress response in these lattices. We also wanted to have a variety of unit cells. And so we had a poll question at the beginning on stretch-dominated lattices versus bending-dominated. And one of the common tools or methods for building a stretch-dominated lattice that might be conforming to a geometry is to essentially take a mesh, but just connect the nodes of a mesh, as shown up here in the top. And some of these, based on the strut thickness, they may actually be a bending dominated, but for the most part, you get lattices that were primarily driven by stretch and buckling behavior. And what tends to happen with stretch dominated lattices or strut based lattices is that the part eventually will suddenly experience buckling. And once it experiences buckling, the stress that it holds will all of a sudden jump down and decrease. But then another strut of another layer might then begin to buckle as well. And you get kind of this jagged response and plateau stress, which may be well behaved, but oftentimes might jump up and down along this, this compression curve. And what we wanted to have in some cases for good crush energy absorption, we're bending dominated cells that have a much smoother plateau stress. They typically have a lower plateau stress, but at least it's well behaved. And from an engineering perspective, that's a nice feature to have. And oftentimes these bend dominated lattices are oftentimes these triply periodic minimal surface type unit cells that some of you may be familiar with, like a gyroid unit cell. But as you can notice, these unit cells are not associated with the nodes of a finite, of like an element. So you can't just connect the dots as we did in these previous models. So we wanted to be able to have a geometry compliant, a lattice structure that would follow geometry, but didn't have to only be a node to node or a strut based lattice. We wanted to be able to support any of these lattice types. There's also a simple fact that as I was trying to build parts or design parts to then run material tests on, that commercial tools of the time, as you can see on this log plot here, tended to have poor performance as the number of cells increased largely, or as they increased. So as you can see, at around 10,000 unit cells, the commercial code that I was using at the time took upwards of 10,000 or 20,000 seconds to compute a lattice. In my original research code, which I wrote in Julia, just some of the inherent benefits of having this compliant mesh, and we'll talk about like where we get this from. I was able to use finite element code principles, and as you can see, I was able to get 4 or 5 order magnitude speedups in being able to create these lattice structures, even when I would create them with a traditional rectilinear layout. So performance was a big thing as well. And then another big issue I had was that as we would try to take these lattice structures into a CAD software, lattice structures, when you would export them to be able to import them into a CAD tool, like Creo or SolidWorks or Unigraphics, they'd be as an STL file with a lot of triangles, so upwards of maybe 100 million triangles. And they weren't really compatible with the smooth CAD paradigm of these CAD tools. And these STL files are large. They would tend to just eat RAM. They would oftentimes crash these CAD tools that weren't really meant to be handling all of these triangles. And this has gotten better over the last few years as additive manufacturing has proliferated. But still, it seems that the lattice structures, especially when you have many unit cells, didn't seem compatible with some thrusts in the model-based enterprise. So enter Coreform Lattice GC, as well as the research codes that led up to it. The general framework for how lattice structure, or the core technology is called geometry compliant lattice structures. So the GC of Coreform Lattice GC comes from geometry compliant. The general framework is to start with a CAD model of your lattice region, or create a lattice region volume within your CAD model. To then prepare that CAD model for mesh generation. So you might do things, in this case, we're going to build a hex mesh. So we web cut or partition our geometry to permit a nice structured hex mesh. You might also do things like defeature or use virtual topology, compositing of surfaces and curves to ignore certain features to be able to get the layout of mesh elements that you want. So in Coreform Cubit, we then build this U-spline mesh. And then kind of at the same time, we're selecting or designing a unit cell that's then going to take the geometric mapping of each finite element or each U-spline element in our mesh to then map it to a deformed configuration of these unit cells that then comply or are compliant to the underlying geometry. And then we can 3D print the result. And this is actually a part that was printed. It's about an inch in diameter out of 316L stainless steel. So this is the general overview then of this process. And as a kind of a keynote, again, what's happening under the hood is we're just borrowing a lot of concepts from finite elements. So we take the geometric mapping of a finite element, and I've shown here the unit cell as a tessellation of triangles. So each point in this tessellation has a mapping then to the element in its deformed configuration when you've meshed the part. And so we just grab that exact same function or mapping to deform each unit cell. And so the key is that because it's a volumetric parameterization and mapping, it's not restricted then to those node-to-node or strut-based connections that we previously talked about, which might connect, say, this node to this node and this node to this node, which is where you get those strut-based structures. And so then just a few of the high-level benefits then before we dive into the demos and some of the capabilities. So essentially, if you can build a U-spline in Coreform Cubit, you can create a lattice structure that inherits the layout of that U-spline. It does also mean that right now we only build these lattice structures on U-splines that can be built in Cubit. And so the capability of the amount of U-splines you can build is then closely coupled to what U-splines we can build, and that drives the lattices that you can build. So right now that's limited to hexahedral swept meshes, but we're rapidly adding more types of meshes that you can create U-splines out of. You can create effectively an unlimited amount of lattices. We do provide 4 that are standard, but we provide a mechanism for you to create your own lattice type or modifications of these original 4. Again, that they're uniquely smooth, which they inherit from the U-spline mesh that can also have this smoothness property between U-spline elements. And then we've also implemented a native slicer that utilizes the inherent structure of the U-spline mesh to then slice these lattices in parallel. And right now we currently export to the CLI format, which is a common layer interface format. And there's a human readable ASCII format as well as a binary format of this. And we export the binary CLI format. And most professional additive manufacturing pre-processing tools, such as Materialize Magics, can import the binary common layer interface. And we're interested to hear what other kinds of slice formats you might use so that we can export to those. All right, so now I'm going to go through a few live demos. So the first live demo that I'd like to walk through is just preparing some lattice parts in Coreform Cubit. So if you attended last week's webinar, you may have seen me run through this example, which is a simple example where we're going to build a lattice on this interior region. It's this yellow volume. And so you just to connect some of the dots, at this stage, we have done the CAD model of a lattice region. We have a CAD model with our lattice region here modeled in yellow. So I'm going to go ahead and prepare this region now for meshing. So stage 2, prepare. One of the things I can see is that I've got a surface that's split in 2, which would mean that if I were to build a mesh that might be, say, very coarse, So let's just start with a very coarse mesh just to demonstrate. You can see that it's going to force an element to respect this surface, because that's how the Cubit meshing software works. And so it's going to drive maybe a really small element that you may not want, or it might drive a layout that you may not want. So we're going to remove this splitting line by compositing these two surfaces together. So to do that, I'm going to go to my mode geometry, entity surface, action modify, and then I select composite from the dropdown, and I select these two surfaces to composite together. I want to show one more thing when I do this. Let me, if I make the vertices visible, we can see again that there's these vertices. And when we do this composite, it will also, this checkbox here will composite the bounding curves. And that will remove then the vertex or the vertices on the top and the bottom of this curve. And so now when we build this mesh, again, we're going to build this very coarse just to demonstrate this. You can see that it doesn't require an element to be conforming to this that surface that had been there. And so now we can get a very large element if we wanted to. So this geometry, Cubit automatically determined was a sweep mesh. Recall from our last webinar that we currently only support building U-splines on swept meshes. And so to ensure that, we're going to, in our meshing module, we're going to make sure that we have selected the sweep option and that we have a source surface that sweeps through to a target surface. I also like, especially for lattice structures, to use the extrude option with redistribute nodes on when I do sweeps. And I'll show you why in a little bit. What I often like to do though, is I often like to then start by first meshing my source surface to make sure I've got the layout of my sweep that I want. And so again, we have many surface meshing techniques in Cubit, such as pave. We might want to choose an element size that's maybe probably, let's do maybe a size of 5, maybe a little bit larger, size of 10. And I might choose a pave mesh to mesh on this surface. If I want to remove some of these extraordinary points, I might choose the clean up extend option for this surface, which removes a few of those extraordinary points. But I can also choose any other surface mesh scheme that might work. And so I actually find that this geometry works very well with a polyhedron scheme if afterwards I apply mesh smoothing onto. And actually, I think what I've done, I may have actually, I believe I did one other thing. Let me just pull this up. That I actually split this geometry. Yeah, so let me actually split this geometry. So we did compositing, but now I'm going to partition the surface even further. So again, in my preparing the CAD model, I'm going to split curves. So I'm going to get a dividing curve that divides maybe these faces in halves. So I can take a curve, modify partition, and cut it in half. Or actually, I guess this is what I do. I add a vertex on this curve. So let's go on curve. I'm going to select these two curves and choose at their midpoints to add a vertex. I'm going to add one on this curve as well. So I've added a few curves. I might on this curve then choose to create a vertex as close to the vertex I've created on this curve down here. Which is vertex 95. And I can then partition this surface between points. You can see that now created a partition here that my mesh elements would line up with. And so now as I mesh this with various different schemes, I can get out different layouts. So once we've created, however we want to partition our geometry or create or unpartition our geometry, it's kind of fully up to the user for you to be able to decide or dictate how you want your mesh to look. So just as some results we can get out of this, I've pre-baked this solution here with the polyhedron mesh. Again, I had done some splitting and then compositing after the fact to get out this this mesh. And we can show, if I put in some lattices, again, we can see the layout of these lattice structures within these cells. If I now turn off the U-spline mesh, we can see this lattice layout. And we have this, we mentioned that there are different types of elements that we support, or of unit cells we support. We have this jack as well as an octet truss cell as well. We also have a truncated sphere unit cell, which is a bending dominated unit cell. And then we have another unit cell that's a self-supporting unit cell called PVB. It'll take a little bit for pair of you to load this up. But it's also a strut-based cell, but it's on the interior. So it's not node to node, but it's essentially cell face to cell face. So the other example I'd like to show or demonstrate in even a bit more detail on is, let me see, something open here, is this Alcoa bracket, which some of you might recall from there was a competition for topology optimization and lightweighting of this bracket. But we can build a lattice structure in this as well for lightweighting. And so in this case, again, we've partitioned our geometry for lightweighting. And what I'm going to do now is, just in the sake of time, I'm going to run some scripts that automate this process. Let me go through this one by one. So let's see. This should work. Oh, I just need to update my paths. Where did I put that? Alcoa. Anyone? Sorry about the delay here. Again, we start by working with our lattice structure region. So this is a complex region we're going to fill with lattice structures. And so the first things we're going to do is we're going to web cut this into hex-meshable sweepable regions. I'm going to first sweep these surfaces through to chop off these top two regions, and then I'm going to cut. I'm going to slice with this plane here to slice off these two nubs. So these are the regions now that are going to dictate my hexahedral mesh. And so I'm going to imprint and merge the volumes that I've created because I want to have a conforming U-spline mesh to have conforming unit cells. And then I'm going to composite the surfaces on kind of this face of the geometry together into a single surface. So now, again, you can see by the dashed lines that Cubit will ignore those from a meshing standpoint. We'll ignore those where those curves had been. And then define some of my mesh properties. And then I'm going to start by defining a mapped mesh scheme on these two faces that I can then sweep through my geometry, as well as I define a pave scheme for this top volume here. Then I'm going to smooth the geometry using a centroid. So we have smooth options. It's this iron icon, or like an iron to iron things out, smooth things out. I can choose centroid area here, so that's what I'm going to do. That smooths my geometry, or smooths my mesh, I should say. And I'm going to methodically, one by one, mesh each of these volumes. So mesh volume 2. And just make sure I ran. Oops, I skipped a command or two. So let me just come back here and get to that. So I'm just going to rerun. I have a journal file that I've prepared for this. Here we go. I'm going to then mesh these other 2 volumes. As well as then these final 2 volumes on the other side. Once we've built our mesh layout, we can build a U-spline. And so right now we build U-splines only through the command line. We don't have a GUI interface for it. We can set our U-spline degree and continuity and build it. And in the sake of time, I'm not going to run those commands. Maybe I will, but maybe I'll do this. I'll open up another Cubit. So first we do is we set the U-spline parameters on the volume. And then next we build the U-spline. So set U-spline on the volumes we want, degree 2, continuity 1. We build the U-spline as U-spline 1. And then finally, there are some commands to export the U-spline lattices. And just what those commands are. So I show this. So we have a command called build U-spline lattice. So once you've built a U-spline, you can build a U-spline lattice with a unit cell that is one of either jack, octet truss, PVB, or truncated sphere. Or you can feed it your own custom unit cell with a tessellation file path. And I'll show that in a little bit. On the base U-spline ID, so base spline ID 1. And then if we want to slice, this is where we can tell Cubit how many processors, I just want to go directly out to slices. So how many processors do I want to use? So I might say like J8, and then a separation between each slice plane. So you might choose like 0.01. We're in the models I've been building have been in millimeters. So this would be 0.01 millimeters, so 10 micrometers. As well as then telling you what the file name of the CLI file is going to be. So we'd say file name, my Alcoa slices. .cli. So we can see that here, if I've built now this U-spline, I'm going to go ahead and copy in these commands. Let me make sure that, in the sake of time, I might choose this to be a bit of a larger separation size. Unit cell, if we say do like jack, then that has now sliced this unit cell or these lattices into the CLI file. I don't have any way to right now to visualize this CLI file for you, unfortunately. This is a file we provide to our existing partners right now, but you can open this up in most commercial slicing tools. You can also export, if you just want to see the lattices, you can export these to ParaView by, instead of doing the slicing, you can run this option for file name for VTK viz and feed in maybe my Alcoa lattice.vtk with the visualize only flag if you're only exporting this visualization. What that allows us to then do is then see the lattice structure in something like ParaView. You can see how it fits in with the rest of your geometry. If you wanted to get this VTK file out to and here I've actually exported these to OBJ files as well. We offer two tessellation exports, both VTK and OBJ. From ParaView, you can take either of those files and you can save the data, and ParaView will then let you export out to the STL file format if you wish. If you're unable to open either OBJ or the VTK files in your own additive prep tool. And if I then wanted to export the rest of my geometry for slicing, we would import, again, this solid model of our solid region, and then choose export to maybe our STL. We might call this the Alcoa solid region. And then choose to export just this last volume of volume 7. And then again, whatever kind of fastening we wanted to export there. In the future, we're working to add the ability to slice these solid models as well, so we can slice both the lattices and the solid models at the same time. So right now we only support slicing the lattice structures directly. Last thing I'd like to show is how you can create your own unit cells. So what I've done is in a separate modeler or in Cubit, I've designed a unit cell. This is the Ashby unit cell from the kind of famous book by Michael Ashby that I've designed and parameterized. If I open up a new Cubit here, we're going to go ahead and, in this Cubit, import that solid model of the unit cell. So here I've got an Ashby unit cell. It's important that your unit cell, and this is all documented in our documentation, but it's important that it's centered at 0, 0, or so at the origin, and its extents are -0.5 to +0.5. So I'm going to do two things to ensure this happens. I'm going to first move my lattice to coordinates 0, 0, 0. That moves the centroid of volume 1 to 0, 0, 0. And I'm going to then scale this model. And I'm going to use A-Pre-Pro formatting here with the curly brackets. It should be 1/50, I believe. And yeah, so now you can see here that it extends from -0.5 to +0.5 in all three directions and is centered at the origin. We then have a command for creating essentially the repeat unit cell of this unit cell. We call that folding this lattice. So we have a command called fold U-spline lattice. We tell it the reference geometry is volume 1, and we're going to tell it to kind of default mesh the tessellation here. So if I run this command, you can see it's essentially found the symmetry of our unit cell. And it's gone ahead and created this initial tessellation. If you want a finer tessellation, you can remesh the surfaces in this group that's called folded surfaces. And then lastly, we're going to run this export U-spline lattice command again, but this time instead of exporting our U-spline lattice structures, we're going to tell it a tessellation group name, which is those folded surfaces. And then we want to have this file, it's going to be, we might call this maybe Ashby cell demo with a JSON extension. You'll get an error if you don't include this JSON extension, but this gets saved out as a .json. And then in whatever other tool we were using to export our lattice structures or build our lattice cells, instead of telling it UC-jack, we are going to tell it to use a tessellation file path, and then the path to our cell, we called it, I think, Ashby, we call it Ashby cell demo.json. And that will then use our Ashby cell. Which we can then import and visualize in ParaView. Or we could have directly sliced this unit cell if we wanted to. Those are the last of those demos. The one more thing I want to mention before we go to Q&A is that we're also working on some projects to integrate these lattice structure calculations with our Coreform IGA solver, which you may have seen webinars for our flex representation method in Coreform IGA. To simplify the simulation of these kinds of parts, especially for nonlinear, highly nonlinear analyses. Whoops. Let me pause this here, this video. So what I'm showing here on the video on the left is this partially body fitted, but mostly immersing mesh that we can use to simulate our solid region, as well as we also use the U-spline background mesh. If I can ever get this pause to work, to provide the immersing mesh for the lattices. And you can see here, some of this are our initial results. We're working on scaling right now with our code, but we are getting out results of these in our Coreform IGA tool. So it's something that I encourage you to keep posted on as we add more capabilities to both Coreform Lattice GC and Coreform IGA. So with that, I'll open it up to questions, if there are any. I'd like to thank you for your attention today as well. Let's see, do we have any questions in the chat? Okay, yeah, very good question. So Clint has asked whether or not we can build lattices that are symmetric about a single axis to be built. And so I think if I understand correctly, maybe like a 2.5D lattice structure, like a honeycomb. Right now in Coreform Lattice GC, we don't have that. that was available in the research code that I had originally written. And so that's one of the next features that we're going to be looking to add, is the ability to add like a 2.5D unit cell, like a honeycomb or like a flow straightener, kind of like, so maybe like a circular holes that they can follow like a pipe or tubing. So, yeah, and so like that would be a 2.5D would be this kind of like a single plane symmetry. I think that's what you're asking. So then we've got. So Clint, let me know if I've answered your question or if I'm still misunderstanding. We got a question from Ron. Will you be able to use the lattice as a geometry that could then be meshed and exported to an FEA solver like Abacus? So at least right now, the lattices that we can export are exported as triangle tessellations. And they'll inherit that tessellation from this tessellation you see here. Now, once you have, say, one of these solid, see if I can actually import maybe a demonstration here. That if we import one of these OBJ files, so we like the jack just for quickness here. And you could export them to an STL file from Abacus, and I believe, or from ParaView, excuse me. And I believe Abacus can import STL files. And Abacus has a tool in its mesh mode. I think it's like mesh edit. So it's like the edit tool. And there's a try to tet option, and that can build you a tet mesh in Abacus. Hex meshing with these is really challenging, but we are working to try to find ways to support kind of automatic hex meshing of these unit cells as well. So if that would be something of interest to you, we'd like to hear more about it, about what your interests there are. But yeah, there are ways to get these lattices into Abacus. Again, you might be paying some of the cost of that you have a lot of surfaces and a lot of triangles and large files. But yeah, that can be done. It's like, let's just do this just as a quick. So if I take this VTK file of this, let's do, of the PVB here. Oh, nope. So if I take this VTK file, let me save this as a, let's call this test.stl. And then we'll import this STL file. The other Cubit looks like it's just rendering now. It looks like it's finished importing though. But that would be the process there. So hopefully that's helpful, Ron.
Greg, we have two more questions that have come in the chat. So the first one is, can you zoom in on the difference between the hex mesh and the U-spline? Does the outer boundary of the U-spline conform to the original solid more than the hex mesh did?
Yeah, that's a great question. So there's a couple ways to answer that. One is that let's do this. Let's delete, just so we can see what this volume is. So hopefully this helps give you kind of some insight to how well this matches or doesn't match. You can kind of see the original CAD geometry outline here. If I set, do graphics. So you can see the original hex mesh, especially on curved portions, does not capture the geometry very well, right? The nodes do interpolate, but it doesn't really capture the in-betweens. Right now, we use a technique called Bezier projection with our U-splines. We aren't building rational U-splines yet. And so these are technically just an approximation to the original CAD geometry because they're polynomial as opposed to rational for like these cylindrical faces. We are working on rational U-splines as well. But so they are a better fit to that. But the U-spline lattice, the lattices, you're right to point out that they will fit exactly to this U-spline. As we get better with matching the U-spline either arbitrarily close or exactly to the original CAD, these fits will become better. But yeah, thanks. That's a very astute observation, a very good question. So thanks for that,
Thank you.
Randall.
Right.
And there's one more question if we do have some time still.
We have a few minutes. So we have a question that came in through the chat. I don't know if you can see that. I can read it to you.
Yes.
From Ada.
Yeah, from Ada. Yeah, so I'll read this for everyone's benefit. Ada has a question about the deformation of a geometry and mesh. If he has built and meshed a lattice cell, for example, a cubic shape or an octet, and he now wants to stretch it in a specific direction, he might think of it by multiplying the coordinates with a transformation matrix. He's wanting to know if this is possible to do in Cubit. Yeah, so this is actually something that I did. I made some test samples back in the day. Oh, and so by the way, Ron, so we've now imported the mesh back, so we could build our tet mesh from this if we wanted. And again, that could be in Cubit. But to Ada's question, let's say that we had a cylinder. And so Ada, as I do this, let me know if I'm answering your question well or not. So let's create a cylinder of maybe height 4, radius 1. And let's put a nice circle mesh. And then let's do ball 1 size 0.2 just for speed. Oh, and delete mesh, surf all size. That should, oh, I guess I want 0.4. All size. Maybe 0.5 is fine. So what we could do is, say we have the cylinder. Well, first I need to split this so that I've got a line between these 2 points. So split periodic vol all. So if I've got some curve here, I can mesh this curve with a bias. So I could define this curve instead of having uniform elements throughout. I could say that maybe I want to have first size and last size. So maybe I want to start with like 0.1, maybe the last size to 0.3, and start from maybe this vertex. And so you can see that would then kind of squish, the elements. Maybe let's actually maybe do like a 0.25 to 1 actually. Here. And then if we were to build our mesh here, mesh ball 1. So you see this would be kind of your stretch. I've got, this is the redistribute nodes thing, but just the stretch that I've created is what does is what would let you stretch your lattice cell. So hopefully I answered your question about how you might kind of stretch that in a given direction. So let me know if that's what you were thinking, or if I've misunderstood. Yeah. So yeah, if you wanted to change node So let me see if I understand, Ida. Are you asking on the base unit cell that we've maybe defined here that you want your unit cell itself to be squished, or do you just want the resulting lattice to have this this stretch? Okay. Yeah. So if you want it on the unit cell, yeah, what you would do is I would create your unit cell still in kind of like a rectangular shape and create it the shape that you want it, and then apply a scale factor afterwards to then create your unit cell that then has some sort of squish to it or of deformation to it. And then that way, you know, whatever your unit cell looks like in this unit cube is what that base unit cell is going to be. Julia has asked whether or not we need to merge each single cell to another. What I'll say is that these, and maybe Mitch, if you want to chime in, these should be, they inherit the continuity of the underlying mesh. So even though it doesn't look like it, right? I mean, these cells, they are already merged together and united. And so we inherit the smoothness, which means there's already at least C0 continuity between the cells. And that's how we get these cells already merged to each other. And that's one of the things that I talked about, like the performance in the past that would take a long time. That was one of the things that that led to this development in the first place. Randall's also asked, or so I guess, let me know if, Julia, if I've answered your question. Randall has asked whether or not we can scale the thickness of the unit cell beams and walls based on some factor or map. And so the answer is not yet, but we are working on that. We are working to add implicit definitions so that, say for this, if we start with our unit cell, so like this truncated sphere, for instance, just going to create this real quick. R 0.55, R 0.6, 3, and then let's do a subtract fall 2 from, or fall 1 from fall 2, 3x1, intersect fall all. So if this is like your solid unit cell, it already has some thickness to it. If we actually create, say, a mid surface between these two faces, we have like some surface, and we can actually now define thickness off of like the face normals. That's something that we're working right now. It's in development, but both for surfaces as well as like strut-based unit cells to have a defined thickness of the unit cells boundaries. And we have some preliminary research that we've done there. So yeah. Great.
Well,
I think we're out of time.
Yes, we'd like to thank everyone for joining us today. Thank you for participating. Thank you for your questions. Please notice when you exit this webinar, a browser will pop up with a survey question for you. It really helps us if you answer those. It helps us to know what our customers are interested in and how we can serve you best. So please take a second and answer that.
Now, I'll mention one more thing. I'm going to add to our forum at forum.coreform.com. I'm going to add a tag for Lattice GC. And if you have any questions that we didn't answer, or if you're interested in learning more, feel free to send us a message here on our forum and ask, and we'd be happy to answer. You can also always email us at support@coreform.com. But anyways, thanks everyone.